Now let's consider weak acid and bases. As I told you, most acid and bases are weak, and uh, these are the basic equation, dissociation equation for weak acid and bases. Okay. In weak acid dissociation, you don't need to write the water. Okay. It is given by this simple equation, and dissociation constant in this case is equilibrium constant is called the dissociation constant. Okay, is given by this equation. But to write the dissociation of a weak base, you have to add water, because except for several strong acid, okay, weak base weak bases don't usually contain hydroxide ion source. Okay, but the weak base now accept protons from this water. Okay, generating hydroxide ion. So the solution uh, becomes basic. Okay, so this is the dissociation equation. Okay, so Kb equals, okay, this one, this ion multiplied by hydroxide and divided by this equilibrium constant of a base. Okay, and the pKw by definition is minus log Kw, is given by this one. pKa is this is a p function. Okay, and minus log Ka and given by this one. And pKb, okay, is minus log Kb. All right. Well, here uh, mm, now consider formic acid and benzoic acid dissociation in water. All right. For formic acid, the structure is very simple. So Ka value is rather is large. Okay, pKa equals by taking the logarithm, negative logarithm of this value, which is 3.744. Okay. In the meantime, benzoic acid. Okay. This is also it's a weak acid. Okay. This one, this proton is dissociate. Okay, and Ka value is like that. All right. So here, the larger Ka, okay, if dissociation constant is larger, and then the pKa value becomes smaller, because from the definition, okay, of p function, yes, since we put here negative sign, okay? So larger the Ka, smaller the pKa. All right, and you see, this is a weak acid. Okay, and then this one after dissociation, this is conjugate base of this one, this weak acid. Okay, and then we can write Kb for this formate. Okay, likewise you can write Kb equation for Kb for benzoate. So the relation between Ka and Kb for conjugate pair, after you calculation, you'll know that Ka multiplied by Kb equals Kw. Okay, this is very important relation. Okay? So uh, once you know Ka, or once you know Kb for the weak base, and then you know the other constant. Okay, for example, for this formic acid, Ka is this value, right? And then what is Kb for formate? And using this equation, you simply you divide this number by Kw, which is 10 to minus 14. Okay, yeah, that's very important relation. And also more important is this sentence. Okay, weak is conjugate to weak. All right, what does it mean? Weak. This one, formic acid is weak acid since this Ka is small. Okay, what about the formate? Okay, this one, this is weak base or strong base. you may think that, oh, formic acid is a weak acid, and then its conjugate base must be strong, but that's completely wrong. Okay, this is also weak base. Here, weak is conjugate to weak. Okay, another. Here, benzoic acid is a weak acid, and its conjugate base benzoate is weak, not strong. Weak base. All right. Yeah, that's very important. Hmm? Yeah, let's read these two sentences. Okay, the conjugate base of a weak acid is a weak base. The conjugate acid of a weak base is a weak acid. But let's see. But order of weakness is reversed. In other words, look at these two species again. Formic acid and benzoic acid. Which one is the stronger? Okay, among these two. Although they are all weak, but formic acid is a little bit stronger, a little bit strong acid compared to benzoic acid because Ka is larger than the that of K the for benzoic acid. But what about the conjugate base? Yeah, formate, benzoate. Which one is the stronger base? Okay? In this case, benzoate is a little bit stronger base than formate. Okay, so that order is reversed, right? Okay, very good, very good. Okay, here. Your textbook shows a very peculiar, rather complex molecule. Okay, this one. I don't know the name for this one. Here is the name. Pyridoxal phosphate. Okay, this is rather complicated, and there are 1, 2, 3, 4 protons that are uh, dissociated in water. Okay, 1, 2, 3, 4. So we can expect this molecule has 4 equilibrium constant Ka1, Ka2, Ka3, and Ka4. Okay, we don't know yet which protons are more easily dissociated. Okay, we don't know yet, but let's see. In this book, the author Daniel Harris, you see, consider fully protonated form. Okay, and then the dissociation constant for the compound is K1, and then next one is K2, like that. All right. In other words, considering this one, starting point is the fully protonated one. Okay. Of course, the full protonation occurs in a very very acidic condition. Okay. Anyway, when fully protonated, this molecule takes this form. Okay. Yeah, this form, and then among 4 protons, which one is the strongest one? The strongest, more easily, most easily deprotonated. Okay, here, POH, this one, POH, yeah, this one of these. Yeah, yeah, these protons are equal. Okay, and one of these is easily protonated, and then in the case pKa is only 1.4. Okay, Ka is 0.04. Okay, and then which one is the no more easily dissociated? OH, this one. Okay, this one is the second easily deprotonated, and then third one is this one, this proton. Okay, it says POH, and then finally this one, this proton bound to the nitrogen is the least acidic proton. Okay, yeah. But this one is when fully protonated, it takes a positive charge. What is the neutral charge, neutral species? Okay, this one, this proton is deprotonated. Yeah, this is a neutral species, but yeah, Harris don't represent this one. Okay, he represent fully protonated form. Okay, this one. All right, and likewise, this piperazine. This is piperazine. Okay, the neutral form, but in the appendix, this is not fully protonated form. Yeah? The fully protonated form is this one. Okay? Two protons are, they bound to nitrogen. Okay, like that. This one. This structure is shown in Appendix G. Okay, don't be confused. Okay. Okay, let's consider the weak acid equilibria. Okay, let's consider, this seemingly, very similar molecules, right? This one is ortho hydroxy benzoic acid. Okay, this position is ortho meta para. Okay, and this one is para hydroxy benzoic acid. Okay, and this carboxyl proton is easily dissociated. Okay, so pKa for this also hydroxybenzoic acid is 2.97. Okay, this is weak acid but relatively strong. Okay, weak acid. Okay, and for this para molecule, pKa is 4.54. Okay, so dissociation constant is different. Okay, why? What makes this difference? Although structure, chemical formula is exactly the same, yeah, but only difference is that this hydroxy group attached on different position. Okay, the explanation is given here. Okay? And in the also form here, when there's a carboxyl proton is deprotonated, this one negative charge is what stabilized by this hydrogen bonding. Okay, so also form makes this kind of hydrogen bonding. You see, this is kind of a hexagon. Okay, but the for para hydroxybenzoic acid, uh, such a hydrogen bonding doesn't take place. Okay, so this anion cannot be stabilized. That's why this ortho form is more acidic. Okay. Well, here is the two typical weak acid problems. Okay, pH. Let's consider the pH of a solution of weak acids. Okay, so in this case, you have to consider charge balance and mass balance. Okay, in the case of HA, yeah, this is weak acid, and from charge balance, so some of the positive charges is equal to some of the negative charges. Okay, since there is only one positive charge, which is proton, and there are two negatively charged species, which is anion A minus and hydroxide ion. Okay, this is a simple charge balance equation, and mass balance equation is what from the former concentration. No, this is total concentration, okay, of this acid. F equals equilibrium sum of the two equilibrium constants, A minus and HA. All right. So equilibria from here we have another equation, and automatically water dissociation, and we get this one, this equation. So how many equations? How many are unknowns? Equations are four. 1, 2, 3, 4 unknowns, and proton, anion, hydroxide, and this one, HA. So there are four unknowns. So this one will be completely solved. Okay, but actually, uh, the solving these equations is not a simple matter. Okay, yeah, but we can have a very good approximation. Although HA is weak, acid, but compared to uh, the proton concentration and hydroxide concentration, yeah, this proton concentration is much higher than hydroxide. So in this case here, this OH minus, this one may be ignored. Okay, or since the dissociation of HA is very small, so the here uh, HA original, the HA concentration may be much larger than this one, proton concentration. Okay, or HA is much larger than OH minus. All right, and then here we can we can ignore here hydroxide ion, and so proton ion concentration is more less is approximated by this one. Okay, the same from charge balance. All right, and a minus ion concentration is much larger than this one. Yeah, or proton concentration is much larger than hydroxide ion. Okay? And then these equations becomes quite simple. Let's put proton concentration as x is equal to anion concentration. Okay, and from the mass balance equation, this one holds. So finally, we get this equation. This is a simple quadratic equation. So using this equation, so in general chemistry, you solve this way. Okay, simply assuming this approximation. Okay, so for 0.05 molar solution whose Ka is 1.7 times 0.7 times 10 to minus 3. All right, this is weak acid, but relatively strongly weak acid. Okay, and then what's the pH, yeah, using this equation? And then this is a simple quadratic equation, and then you get two solutions, but one of them has negative sign. Okay, so simply we ignore it, and then by solving this one, x, which is proton concentration, is 6.80 times 10 to the minus 3. Okay, and pH is minus log of proton concentration, which is 2.17. Okay, and then what is the undissociated the concentration of this one undissociated form? It is given by formal concentration minus proton, or this one anion. Okay, and then it is 0.0432 molar. Right, this way we can solve this problem, and to make sure the approximation, this one, and then here we obtained the proton concentration, which is 6.80 times 10 to the minus 3. All right, and so let's see, proton concentration from HA dissociation, and here it gives the same value. Okay, so this approximation makes sense. Okay, and what about the hydroxide ion concentration? From the since we know proton concentration, and from Kw it is calculated to be 1.47 times 10 to the minus 12. Okay, all right, so let's compare these two concentrations. So proton concentration is much higher than hydroxide ion. So here hydroxide ion concentration is ignored. Okay, yeah. So this approximation is a good one. All right. Okay, let's continue. Now let's consider the fraction of dissociation. By fraction. So the range is between 0 and 1. Okay, so the fraction of dissociation is defined by this equation. The denominator is the total concentration, in other words the formal concentration of weak acid, and since it is dissociated, so we consider the anion concentration. Okay, yeah, and then uh, if anion concentration is x, and then it's given by this one. Okay, and this is definition of a fraction of dissociation. For 0.050 molar ortho hydroxy benzoic acid, alpha is what? Since formal concentration 0.05, yeah, and let me see, let's see here. Okay, actually, we consider the equation, the dissociation of this compound, and then we got from here the concentration of A minus is 6.80 times 10 to the minus 3. Yeah, here, okay, and then it is 0.136 and 13.6% is dissociated. Okay, so here, if you keep calculating, the fraction of dissociation depending on the formal concentration, and then you will find the more dilute, the more dissociated. Okay, you see the very diluted weak acid solution. Yeah, it is weak acid is more dissociated. All right, if the weak acid concentration is high and the dissociation is smaller. All right, why? You know, uh, that's why the this equilibrium constant should be maintained constant. Okay, to maintain the equilibrium constant, then dissociation changes depending on the concentration of a weak acid. Okay, uh, but the stronger acid more dissociated at all concentration than weaker acid. All right. Yeah. And here is a sense of a weakest problem. We can put these two concentrations are equal, but for the strict calculation, you don't need actually this assumption. Okay, we solve four equations. Okay, but this simplified equation uh, uh, generally holds. All right. However, here is a caveat. This approximation would be poor only if the acid is too diluted or too weak. Okay, in that case, you have to consider water dissociation, and you have to take those four equations into consideration. Okay, let's look at this figure. Yeah, this figure shows the fraction of dissociation depending on the pKa value. Okay, this one ortho hydroxy benzoic acid. This is a little bit stronger than this one para hydroxy benzoic acid. Okay, and then what about the change of dissociation? This fraction. Okay, let's see. Consider for consider the first this ortho compound. Okay, yeah, it readily dissociate. Okay, as x-axis is a log concentration, log formal concentration. So since it is given by log, so if you go to the right side, and then means what? The concentration is becomes smaller and smaller. Okay, and the general trend is that as concentration becomes lower and lower, more and more dissociation, okay, occurs. Okay, the so fraction of dissociation becomes larger and larger, and then at very low concentration it approaches 1. Okay, fully dissociation. Okay, but this also compound is a strong acid than this para compound. Okay, so it starts earlier. Okay, this curve start earlier. Okay, now let's consider again the weak acid problem of pKa value is small. This one, 3-methyl ammonium chloride, yeah, this compound. When this compound is dissolved in water, this chloride is completely dissociates, and we have only this one. Yeah? This is uh, ammonium ion, right? And it dissociates. This one, this proton, dissociates, but its dissociation constant is small. pKa is 9.799, so Ka is 10 to minus 9.799, and it is 1.58 times 10 to minus 10. Wow, it's very small. So this compound acts, yeah, behaves as a quite weak acid. Okay, yeah, let's assume, the first assume is complete dissociation. Okay, here this is a you know, the we just assumption, and f minus x, okay, x, is dissociated by x, okay, and you can set up this equation, and then we what solve this equation, and then we get the pH of 5.40. Okay, but actually this compound is not, cannot be completely dissociated. Okay, yeah. So we set up this equation. Yeah. So it is not completely dissociated, giving some ionic pairs. Okay, this one. Yeah, ionic pair is that what? It dissolved, but the positive and negative ions are put together and behave as if one species. Okay, and here in this case we can another approximation. You see, let's look at the denominator, 0 0.1 and x. Uh, if we have idea of the small x, yeah, if x is quite small compared to this 0 0.1, and then this x can be ignored, okay, and then we can very easily solve this equation for x. Okay, in this case x is 3.97 times 10 to the minus 6. Okay, they are the same value. Okay, so another, here we already made one assumption, and here we made another assumption. Okay, as we made more and more assumption, okay, your answer may be very much debated from the true value. Okay, so I recommend avoid this kind of extreme approximation. Okay, here is the rule of thumb. A reasonable rule of thumb in approximation should be less than 1% of formal concentration. Okay, so if you are not sure, then don't make any assumption. Okay, you simply fully take all the equations and solve for pH. Right? That's my advice.